Welcome back. Today we'll be digging into the nitty-gritty details about hypothesis testing, as most frequently practiced, through tests of statistical significance, called p-values or alpha values. The p is for probability, as in the probability that a population with a statistic such as a mean or a regression coefficient outside a specific range of values would have randomly produced a sample like your data. Again, the probability that a population with a statistic outside a range of values would have randomly produced a sample like your data. The p does not mean that the probability that your statistic is correct, nor is it the probability that the true value falls within a specific range, although that's getting closer to the truth. Now, null hypothesis significance testing is basically about how likely it is that your results are random noise, and that's very important to understand. But once we have research in null hypotheses, how do we actually go about conducting and interpreting a test? Well, the first decision you have to make is what value to use as a criterion or a cutoff. The p-value represents the degree of type 1 error, that is, the proportion of false positives you're willing to accept. The most common p-value of 0.05 allows that about 1 in 20 positive results where you reject the null hypothesis might come from chance rather than a systematic relationship. Now, 0.05 isn't a magic number, though. What matters most is the situation. If you're manufacturing airline parts and testing a sample for quality and safety, a 5% chance of type 1 error is terrifying. So you would likely use a 0.01 or even 0.001 or lower value. However, there's a substantial trade-off involved, since the z or t-scores necessary to reject the null hypothesis increase more and more rapidly as the value approaches zero. Think of the relative sizes of the tails of a normal distribution as compared to its center. Also, every decrease in the acceptable level of type 1 error will also produce an increase in the probability of type 2 error, that is, of failing to reject a null hypothesis that actually was false. For many scientific enterprises, though, 0.05 is quite adequate, particularly since every time a finding is replicated with different data, the probability of randomness is compounded, meaning that to randomly get results that were significant at the 0.05 level in 3 consecutive independent trials with different data has a probability of 0.05 cubed, or 0.000125, less than 2 in 10,000 times. One potential way to loosen the criteria a little is to use a one-tailed test, but it's typically ill-advised. Most often, we expect that differences of effects will have a specific direction or sign. For example, that women will make less money than men, not just a different amount of money, but we still typically rely on two-tailed tests that only test for difference, not direction. Why? It mostly boils down to the temptation to fudge a little. As I said before, the criteria are arbitrary. There's something you have to decide. So what if you did a two-tailed test and found a significance of 0.06? It'd be very easy to pretend as if you had a one-tail hypothesis all along, changing the rules after the game had begun. And if you have unexpected findings in the opposite direction you expected, the temptation would be very strong to speculate on the meaning of that direction, rather than simply reporting a null effect of not what you expected. The exceptions, when one-tailed tests should be uncontroversial, are when only one end of the spectrum is substantively important. So a gambler might want to know what the probability of breaking even is. As long as they don't believe they'll lose money, they keep playing, so it doesn't matter for that decision whether they're likely to win $1 or $1 million. Now, often scientists will test multiple results in the course of a single series of analyses, like one paper. In fact, this is probably more common than not in sociology. Unfortunately, the probability of finding at least one significant finding due to type 1 error, that is, at least one false positive, increases every test you add. So for 2 tests, the probability almost doubles. For 3, it almost triples. For example, a 0.05 probability of type 1 error in a single test leads to a 0.143 or 14.3% probability with just 3 tests. This is sometimes called the family-wise error rate. There is a simple way to deal with these inflated error rates. It's a an adjustment often called a Bonferroni type adjustment. What it does is it decreases the p-values for each test to make the overall probability of any type 1 error equal to the preferred criterion. So each test is stricter because you're doing more tests, so that overall you're expecting the error rate to be 5% for at least one false positive. But of course, this also increases the probability of one or more type 2 errors, so investigators can be wary to use them. Now, hopefully by now you're beginning to get tired of hearing the broken record. P-values are useful, but not perfect. Decreasing the probability of type 1 error increases the probability of type 2 error. The next video will delve more into this last point by discussing statistical power, a measure of how likely you are to find a significant effect in your sample, and with your p-value if one exists in the population. So thanks for watching, and stick with us. Thank you.